So the first type is the transverse waves. Transverse waves are, sorry, my bad. Oh my God. Let's start from the very beginning. Electromagnetic waves. So electromagnetic waves are basically, number one, all transverse. They do not require a medium, like they can go in vacuum as well, can travel in vacuum, and then they all have 3.0 times 10 raised to 8 meters per second speed in air or vacuum. Is it clear, everyone?
Yes.
Okay, now, so few examples of these are light, X-rays, radio, waves, etc. That's some of the examples that we're looking at now. The other type of waves are the mechanical waves. Now, the mechanical waves can be regarded as waves. They can be both transverse and longitudinal. The reason we call them mechanical is they require a medium to transfer energy. Like, a liquid, solid, or gas. They cannot travel in vacuum. Now, some of the examples are sound, seismic, which is the earthquake ones, water, etc. Right? So these waves form here. Now, what we can do is we can represent waves in sort of a say, first let's define transverse and longitudinal and then represent them. So transverse waves are defined as waves that propagate energy perpendicular to oscillation. So this word is the key word you guys need to remember. What it means is that they look like this. So their oscillation or vibration, right, is like this, up and down, and the energy transfer is like this. Okay. Some of the examples of these are light, water waves, and in earthquake they could be seismic, S waves, so S component of this is transverse. All right. These are just examples. They might ask you. You can no. All right. If you have not written something, please do let me know. I can stop and you can write it down. Okay. All right. Should I go forward then?
Sure.
Okay. Now, the next type is the longitudinal one, right? So longitudinal waves can be regarded as waves that propagate energy parallel to oscillation. Okay, so what it means is that this is the keyword. So in these kind of waves, you have like areas where the wave is really close and then areas where wave is really far. So close, far, and like close again, and close, like this. So this is the reason why this oscillates, vibrates to and fro, and the energy is transferred parallel to the vibrations. So the examples of these are sound, you can also generate them on a slinky spring, also seismic P waves could be longitudinal. All right, if you have any questions, do let me know, okay? Okay. Now, so what you guys need to understand now is that we can represent these waves on a graph. So it's represented like two different ways. First, you will have displacement on the y-axis, and then on the x-axis you have distance, and you can create the wave. Okay, I'll also like to copy this, maybe you need to use it later. Okay, so the top points that you see, these are called crests. This is also crest. This is also crest. The bottom points are troughs, trough, trough, and trough. Okay, is it clear?
Yeah.
Yes.
All right, now. So, the first thing we can find using a wave, this is given by displacement distance, is wavelength. And wavelength can be defined as length, or let's write distance, between two successive points on a wave that are in phase. Now I'm gonna explain this word in phase later. But right now, you should remember that the symbol of wavelength is lambda, and the SI units of wavelength are meter, and this is a scalar quantity. Right. Now, so between a crest and a crest, if you try to find the length, that is 1 lambda. Between trough and a trough, this is also 1 lambda. And if you could just go through one whole crest and one whole trough, that's also the same distance as lambda. Okay. Okay. Now, the other thing we can find is the amplitude, and the amplitude is the maximum displacement of a wave. So now, the SI, the symbol of amplitude is A, and the SI units, because it is displacement, it is meter, and it is a vector quantity. The reason is that it's displacement, and you can find it like from this position, this line, which is the mean or equilibrium, right, of a wave. From here you can go to the top like this to find amplitude, or from this to a trough, that is also amplitude. Understood?
Yeah.
Good. All right, now, so then what you can do is, if you guys have written it, should I go forward now?
Yes.
Okay. If you plot a wave with respect to time, okay, instead of distance, you have time on this side in seconds or whatever. So this is basically the crest, the trough, So from this kind of wave, which is given against time, we can find the time period. The time period is the time taken to complete one oscillation. You can also call one wave, want to. The symbol of a time period is capital T. The SI units are seconds, and it is a scalar quantity because it's just time. So time period can be found out exactly like we found wavelength, like from crest to crest. That would be one time period. From trough to trough, that is also a time period. And this is also one whole crest, and a trough is also time period. Okay. Now, once you've done with the time period, then you can find the frequency. And frequency can be defined as number of waves produced in 1 second. The symbol we use for frequency is F. The SI units are hertz, which is Hz, which is also, you can write it as 1 upon second, that's the same thing. It's also scalar. The formula that connects frequency and time period would be F equals to 1 upon the time period. Okay, done. Is that clear?
Yes.
Yeah.
Now, so from here we can actually derive the wave speed. The wave speed is like, because speed is distance over time, for one complete wave, the distance is equal to lambda, and the time is equal to the time period. Okay, so it means that we can do we can write speed. Wait. Okay. All right. So now, because speed is distance over time, so we can write, instead of distance, write lambda. Instead of time for one wave, it is lambda by t. So speed would be lambda over t. And since frequency is 1 upon t, so we can replace 1 over t with f. So this will become v equals to f lambda. That is the general equation of speed of wave, like that. All right.
Here.
Good. All right. Now, we'll move to basically this part where I said in the wavelength definition, I said the distance between two successive points on wave that are in phase. So now we're going to move towards understanding phase and phase difference, because other things you've already done in O levels as well, but this is something new. Now, so I'll try to explain this with a circle, because when you complete a circle, that is also considered as one complete oscillation. Okay. Suppose this is the displacement and this is angle theta. And we're starting from this point right here. Let's call this A. So when A is here, we are here, and we'll segregate it into 0 degrees, and then 90, and then 180, 270, and 360 degrees. Okay, like that. So let's suppose you're moving like this. So when you move to point B, you go a quarter of the circle, which is 90 degrees. Do you understand? This means that now at 90 degrees you're at this level. So you were at 0 here, and now you are gone like this. Now in the next 90, now you reach 180 degrees, and now again you are at this level. Okay. Then when you go here at point D, so you've reached like another 90, so it's going to be 270 degrees, which means it's like here, like that, because D is here, right? And then when you reach back to A again, so you travel another 90 degrees, and now you've completed one whole oscillation, which is of 360 degrees. Do you guys understand how this wave is formed?
Yeah, I got it.
Okay. Now, if you see in 360 degrees, one whole wave has completed. Now, for that, we can say that 360 degrees is equivalent to one complete oscillation. That also means that this is also equivalent to, like, one lambda is also one complete oscillation. And even one time period is also equivalent to one complete time oscillation. Okay? Ikra, do you understand? Ryan?
Yes.
Okay, good. It means all these things are happening with respect to each other, parallel to it, right? At the same time. So, what we can do is we can actually plot them side by side as well. Like, let's try and do that. Like that. Okay. So I'm gonna put them right here. So suppose all of them have displacement x on this side. So let's call this x, let's call this x. This one is distance, this one is time, and this is with respect to angle theta. So what you guys need to understand is that when it is 0 lambda, 0 time, 0 angle, at exactly this point, when it is a quarter of lambda, this point is also a quarter of time period, and the same point is when it becomes 90 degrees, right? Then when it reaches this point, this is basically half lambda because it's half wave. This is half time period, and this is 180 degrees. This point is 3/4 of lambda. This is 3/4 of time period, and this is 270 degrees. And this point is one whole lambda, which means the whole 4/4. This is one whole time period, and that's when it is 360 degrees, and it can go forward as well. So what we can achieve from this is that 360 degrees is equivalent to a lambda and a time period. Okay, do you guys understand this? So because all of them are happening at the same time, that's all. Okay. Okay. Now, so this basically what you understand is that the phase is like the position of anything at a particular point on a wave. Okay. So if you understand this and you draw this, then we can move forward to phase difference, and I'll try to explain what that means. Okay. Should I go forward then?
Yeah.
Yeah.
Right. So Then let's go to phase difference. So let's try and put wave like this again. Now suppose this wave has displacement here and theta degrees. This is 0, 90, 180, 270, 360. This will be 450. This is going to be okay. I don't want this. I want a bigger one because it would be a bit, congested. Let's make it bigger. Okay, so now let's make it like this: 0, 90, 180, 270, 360, 450, 540. This will be 630, and that's 720, like that. Okay, this is theta in degrees, and that's displacement. Now, so we're looking at certain points. We're looking at A, B, C, D, E, and let's call this F. Okay. Now, first question is, they say find the phase of A, B, C, D, E, and F. Okay. So speaking of phase, then we would say that, okay, fine. A's position on this one got to be 90 degrees. B is at 270 degrees, as you can see. So it's just the position of that point right now. C is 360. D is 540. E is 630. And F is 450. Do you guys understand how I
Yes.
got this?
Yeah.
Right? So you just need to look at the position. Now they say, part A, part B, they say find the phase difference in A and F, F and E, and B and C. So this is the question. So what we're going to do is, we're going to say, okay, the phase difference between A and F has to be, F is 450 minus A 90. So we get 360 degrees, which means between these 2 points there is a difference of 360 degrees. Okay, like that. And then the phase difference in E and F, that would be, F is 450, E is 630. So 630 minus 450. So you always do the bigger minus smaller. And that's going to be 90 degrees. Sorry, 180. My bad. And then we can talk about the phase difference between B and C. So that's going to be 360 minus 270, and that is 90 degrees. Okay, now what I need to tell you is that if you have a difference of 360 degrees, we call these points in phase. This word in phase. In phase is basically anything like multiple of 0, 360, and then 720, and so on, right? Like that. When there's a difference of 180, we call this as anti-phase. I'll tell you what it means in a bit. So it is like the multiples of like 180 and then 540 and then 900 and so on. Keep on adding 360. And this one, any other angle than 180 or 360 multiples, you can say it's out of phase. So it could be any other angle. Okay. Now, what exactly does this word represent? When 2 points on a wave are in phase, so it means those points are moving in same direction. They have the same speed and they have same displacement. When 2 points are anti-phase to each other, we call they have opposite directions. They have opposite velocity. Also, they have opposite displacement. I'm going to show you on the graph as well in a bit. And finally, when you see this one, anti-phase have, it could have it's different, or it could have same direction at that point. Would be a different speed, and these 2 points have different displacement. Now, what I mean by this is, like, if you look at A and F right now on the graph, okay, let's just write it first. Please write this down, and then I'm going to show you on the graph. Don't have to, you know. Okay, you have written this. Should I go forward now?
Yeah.
Yeah.
Okay. So, if you look at this graph, right, we're looking at A and F. So you see, A and F are at the same displacement right now, isn't it? Also, they have the same direction, as both are going to go down after this, okay? And both will have the same speed as well. Understood? So these 2 points are in phase, and if you look at it, they're both crests, so they also represent 360 degree, and that's also 1 lambda. That's why we say a lambda is something when 2 points in succession are in phase. Do you understand now? the concept behind it?
Yeah, I got it.
Now, let's look at antiphase. So antiphase is E and F. So if you look at E, E is exactly opposite. Like F is on the highest point, E is at the lowest point. So it has opposite displacement. It has opposite direction of movement, and obviously it will have opposite velocity. May have the same magnitude but opposite direction. That's why we're calling velocity. So everything is opposite. That's why it's called anti. And if you look at B and C, so when B is at the highest or lowest displacement, it's going to go up. So C is at zero displacement. It's different, and now it is also, it's going to go, down. It could have different speed. It could have different direction. It could have different displacement. So it means they're not entirely against each other. They're not entirely opposite of each other, but they're different. That's why we call all other angles as out of phase. Okay.